Hey everyone, my name is Vikram Srikanti. I'm a PhD student in the RISE lab at UC Berkeley. Over the last few years, a lot of the research our group has done has focused on bringing performant and easy-to-use state management abstractions to serverless computing. We believe that this is an integral part of the evolution of serverless infrastructure because it's a prerequisite to enable a ton of real-world applications that would like to take advantage of the simplicity and scalability of serverless computing, but are limited by the fact that standard FaaS infrastructure today is purely stateless. The state of the art today is for functions as a service systems to modify application state that lives in a shared storage system, usually a system like AWS DynamoDB or S3, which are eventually consistent. This, however, raises a number of fundamental challenges around fault tolerance that have received relatively little attention thus far. These are questions like what happens when functions fail mid-flight. If a function is writing multiple updates to storage and some of them are persisted, but before all of them are persisted, the function fails, what happens? Or more challengingly, maybe a request is composed of multiple logical functions, and after the first function finishes to completion, there's a power outage or a DNS failure, which means that the second function never gets executed. In both of these cases, the question is what is the contract with the user? Who is responsible for determining that a failure has happened, and for making sure that the functions are executed correctly and that the application state is returned to a sane state for whatever the application's definition of sanity is. What we would ideally like is the most understandable thing, which is exactly once execution, which means that despite any failures, what the application perceives is that each request is executed exactly once. However, the state of the art for commercial FaaS systems is at least once execution, which means that the infrastructure, when it detects a failure, will retry requests, sometimes repeatedly, to make sure that each request is executed to completion once. And cloud providers advise developers to write idempotent applications, which when combined with the at least once guarantee, simulates an exactly once guarantee. However, we all know that writing truly idempotent applications is extremely difficult to reason about. And worse yet, idempotence is often not enough. Because in the interim between a failure of a function and the retry of that same function, the application can actually mistakenly expose partial side effects, which we call fractional executions. So what we really want is not just idempotence or at least once execution, but we want atomic visibility of all of the updates in a single logical request, which means that either all of the updates are visible or none of them are. To take a simple example, imagine two requests that execute in parallel. Request 1 writes updates to keys A and B, and request 2 reads A and B. Let's say that request 1 first writes its version of A, A1, which is persisted in storage. But before it can write B1, there is an error, which means B1 is never written. Even if request 1 is idempotent, which means that on an eventual retry, it will write the same versions of A1 and B1. If request 2 executes in the interim, it will read the new version of A, A1, but read an older version of B, B0. In order to avoid this, what we want is for updates to be atomically visible. Either you read A1 and B1, or A0 and B0. AFT is a system that we've built to solve this problem, and it guarantees exactly once transactions for functions as a service applications with minimal application level code changes. It does this by transparently enforcing fault tolerance by building a Shim layer over existing storage systems like AWS DynamoDB and AWS S3. Under the hood, it implements new protocols for read atomic isolation, which is a database isolation guarantee that ensures that all of the updates in a single transaction are atomically visible. In practice, we're able to impose extremely low overheads compared to standard cloud deployments and also demonstrate that the system is highly scalable, keeping with the scalability of standard FaaS infrastructure. More broadly, AFT is a part of a broader stack we've been building in the RISE lab called the Hydra project, which is reimagining the way that we do cloud programming from the ground up. If you're interested in learning more, you should check out our longer talk for more details, and you can find the link to that talk in the description below. And you can also look at our website at hydraproject.github.io. Thanks for listening.